My name is Mr. Nyaga, your physics teacher from Kiamutugu Boys High School, and I'm going to take you through a physics topic that is in Form 4. The topic is floating and sinking, and I'll take you step by step, and by the end of our discussion, you realize that you'll be able to, one, you state the Akinedis Principle. That's our first objective. Two, we'll be able to verify the Akinedis Principle. Three, by the end of our discussion, you should be able to state the law of flotation. Four, we shall define the relative density. Five, we shall describe the applications of the Akinedis Principle and the relative density. And our last objective, we should be able to solve some of the numerical problems involving the Akinedis Principle. Good morning, good afternoon, good evening, my viewer. My name is Mr. Nyaga, your physics teacher and also your physics mentor from Kiamutugu Boys High School. I'll be taking you through floating and sinking, which is a topic in Form 4. And initially I had given some objectives which we are supposed to meet in this topic. To start with, I'll begin with some instances. We have some experiences which we shall be explaining in this topic. The first one, we have a still very floating on water. A still very floats on water. We know that still is more denser than water, but it floats on water. We shall be explaining the reason why. We also have another instance whereby you take a cork, you know a cork, you take a cork, you try to immerse it in water or any liquid. Then after you immerse it in the liquid and you release it, after some time after you release, you realize that that cork will rise and to the top of that liquid. Another case, we have an instance whereby we have a very heavy stone. You take a very heavy stone, you try to lift it in water and you try to lift it in air. You realize that when you lift it in water, it is lighter than when it is in air. We shall be explaining all these experiences in this topic. So students, welcome, and let's have a look at our first principle here, which we are supposed to know how it states. Our principle is called Akinedis Principle. Akinedis Principle. Akinedis was just a scientist who realized that if you take an object or a body and you immerse it either wholly or partially, the weight of that liquid which is displaced is equal to the upthrust force which that body experiences. That is, if you take a body which is, so it is stated that when a body is partially or wholly immersed in a liquid, it experiences an upthrust force, which is equal to the weight, of the displaced, liquid. So this is the statement of the Akinedis Principle. We have a body which is either partially or wholly immersed in a liquid. You immerse it, then the upthrust force which it experiences will be equal to the weight of the displaced liquid. So student, that is the Akinedis Principle. Now, we will verify this Akinedis Principle both experimentally and also mathematically. So expect our discussion to be very interesting. So to start with, I'll begin with the verification of this Akinedis Principle mathematically. So let's continue. Now, students, let's verify this Akinedis Principle, and also we shall be looking at what causes this upthrust force. To begin with, we have this force, the force at the top of this body here. This is the body which has been immersed in this liquid. This is the force at the top, so we call it Ft. And this is the force at the bottom, we call it Fb. Now, student, let's start with, we know that the force at this top here is less than the pressure. The pressure at this top, at this point here, is less than the pressure at the bottom of this body. So therefore we say that pressure at the top is less than pressure at the bottom. And student, we know that on the top of this liquid here, on this fluid, we have atmospheric pressure. We have atmospheric pressure, which is acting at the top of that fluid. So therefore, what will be the pressure at the top? So to begin with, pressure at the top will therefore be given by atmospheric pressure here, plus the pressure of the liquid, which is above that, that body. So it is density of that liquid times the height of that liquid above. So it is H1 times G. So that is the pressure at the top. And what will be the pressure at the bottom? This one. So the pressure at the bottom, student, it will be given by the atmospheric pressure still, plus the density of this liquid times the height, this height of that liquid, the pressure due to this height, times G. So we have been able to obtain the pressure at the top and the pressure at the bottom. So let's move on and get the force, both the force at the top and the force at the bottom. Now, to begin with, the force at the top, we know that from one pressure, we know that pressure is given by force over area. So therefore, from this equation, we know that force will therefore be given by pressure times what, student? Times area. And now we shall be using the area of this object here, this body which has been immersed in the liquid. So therefore, it will be given by pressure at the top times the area. So when you do that, this formula here, you substitute it from here. So therefore, you will have area times pressure at the top. We said it is atmospheric pressure plus this is the force at the top. And what will be the force now at the bottom? The force at the bottom will be given by pressure at the bottom times area. And we are talking of the area of this body here. So therefore it will be given by area into bracket atmospheric pressure, I'm talking of pressure at the bottom, plus this pressure of that liquid. Now this is the pressure, this is the force at the top, and this is the force at the bottom. Now the resultant force, as a result of the difference between these two forces, we call it a resultant force, which is the same as upthrust force. It is the same as upthrust force. So therefore, student, resultant force, which I'm saying that it is the same as upthrust, will be given by force at the bottom minus force at the top. That will be the same as a resultant force, which is the same as upthrust. So therefore, it will be given by what? You substitute each formula here. So it will be area, pressure, yes, minus this Ft, it will be area P plus density. We have all that formula. We have derived it. Now let's continue. When we subtract this formula from this formula, therefore we are saying it is the resultant force, which is the same as, allow me to represent it as thrust force. It will be given by area times density times G, then H2 minus H1. So you can write it H2 minus H1, student. So when you subtract this formula, you get this, and H2 minus H1 will be the same as the height of that body. So we can say H2 minus H1 will be the same as H. Allow me to call it H here, the height of this body. You allow me to call it H here, which will be the same as H2 minus H1. Now let's move on. Therefore, we can represent this upthrust as upthrust equals to area, density, G, H. So this is the formula for upthrust. But we know that volume, from some mathematics which you know, we know that volume will be given by the cross-sectional area, which is A times what, student? A volume is given by cross-sectional area times what? Height. So we say times height. So therefore we can rewrite this equation as here. Instead of writing A and H, we substitute it with volume. So therefore it will be upthrust is equals to V, A times H. This is the density of that liquid, and this is G. We know that is G. So this is the upthrust of that liquid, student. This is the upthrust, that resultant force. So we can write that equation here. Volume, density, and G. So this is very important. Now, also in the Form 1 student, we learned that the volume of the water, of the fluid which is displaced, is equal to the volume of that body. That is a concept you learned in Form 1, under the topic of measurements 1. The volume of the liquid displaced is equal to the volume of that body. So let's continue. Let's continue. So student, we are talking of the volume. Volume of the body is equal to volume of the liquid displaced. Volume of the body is equal to volume of the liquid displaced. And we have said that the volume of this body is the cross-sectional area times height. So therefore, we write cross-sectional area times height. It will be the same as the volume of the body, which will be the same as the volume of the liquid displaced. So we can say the volume here, volume of liquid displaced, volume of liquid displaced, we say that it is the area times height. That is true. But also we know that mass, in Form 1, we learned that density is given by mass over what? Volume in Form 1. But therefore, we can make M, the mass, the subject of the formula. So M is given by density times volume. So let's continue. So what will be the mass of the liquid displaced? Mass of the liquid displaced, mass of the liquid displaced will therefore be density, this is our density, times volume of that body. And this is the same, this volume is the same as this, area times height is the same as volume. But also we know that in Form 1, we know that weight is given by mass times what? Times the gravity. So mass times G. So therefore, here we have the mass of the liquid displaced. So what will be the weight of the mass of the liquid displaced? Weight of the liquid displaced will therefore be the mass, this is our mass, density, volume, times G. So our G is G. Student, we can see that clearly this weight of the liquid displaced is the same as what? The upthrust. So therefore, that is the Akinedis principle. Weight of the liquid displaced is equal to the upthrust force experienced by that body. So student, we can see clearly that the upthrust experienced by this body depends on one, the volume of the liquid displaced, and also the density of that liquid. So we have verified our Akinedis principle mathematically. Thank you for listening to my lesson.